So in this video, what I wanted to go over was how do we actually traverse a graph, right? So I made an example graph for this, this demonstration. So for this, we're going to use self.nodes as a collection of all the nodes. And we're going to use a dictionary so that we can easily find a node by its name, right? And I'm using strings to have these nodes. So like A, B, C rather than 1, 2, 3. And so, yeah, we're keeping these in a dictionary. And as you can see, when we create a new node, we'll just use that string, like A, to create a new spot in our dictionary. And then we're going to add a list as its value. That list is going to represent the edges. And so you can see when we add an edge here, what we'll do is we'll find the two nodes by their name, and then we'll just append the name of the other node that we want to attach to the list of edges for this node. Okay, so let's go over the graph that I have created so that we can kind of talk about the different behaviors that this subgraph traversal will do for us. So as you can see, A, B, C, D, E, F, and G, I've kind of put them together, Z by itself and X and Q together, but by themselves as well. And that's because of how I've connected them. This is a little bit harder to read, but like A and B are connected, A and C are connected, and they're connected in a directionless way. So A is connected to C, and then C is also connected to A. So to visualize that, which is a much easier way to see it, I've drawn this up. And you can see that we kind of have three distinct subgraphs here in our graph. So you've got this graph where A is connected to D, B, C, and E directly. E is connected to A, B, and G directly. G is connected to F directly. C is connected to D and A directly. And B is connected only to A, D, and E directly. And then X and Q, they're over here on their own by themselves. They're not connected to any of this, right? So it won't be possible for us to traverse this graph and get to X or Q. We also similarly won't be able to get to Z, and we won't be able to get to Z from X or Q because there's no relationship between them. And so what we're going to do is write a subgraph traversal algorithm. You're going to recognize some of the same ideas from traversing trees. Instead of using a stack, though, we're going to use a queue, which is basically like a stack, only it's more like a line, where when people line up, you take the front rather than the back. Okay, so let's talk about how we do this. Well, we have to start with a root because we have to start somewhere, right? And so we need a queue of nodes to visit. And that queue is going to be a list. And in it, I'm going to start our list off with our root node. Okay. And then I need to also keep track of where I have gone so that if there's cycles in the graph, I know where I've been. So anytime you have to deal with this, where you might have a cycle in the graph, you need to keep a list of where you've been. It's kind of like leaving a breadcrumb trail, right? So visited. And I'm going to use a set for this because we're going to frequently look at our list of things that we've visited. And I want it to be really easy. What's the problem here? We're not using them. Great. Okay, so now you remember from DFS what we did, or BFS, what we did is we had this stack of nodes to visit. And so while to visit, and I'm going to use the length of to visit, which is greater than 0. So as long as we've got nodes to visit, then what we need to do is say our current node is our to visit q.pop. And we'll do .pop. We won't pass anything in, or we'll pass in 0 so that you can kind of see where that's coming from. It's coming from the beginning. Pass off, pop up the first thing off the queue. The next thing that we want to do is check to see if our vertex is not in our visited list. So if our node, right, is not in, or not in visited, right? And that's an O of 1 operation. So that's just a simple if statement. We're doing one operation to check to see if that node is in there. And then if it isn't, let's print it, print node. And then also add it to our visited list, because now we've printed it, we've been there. So visited.add node. Okay, so that's how we traverse all of the nodes that we have in our queue to visit. But so far we've only traversed the root node, this sort of base case. So now we need to find the next few nodes to try and visit before we end our loop and terminate our search. So for neighbor in, and then here's where we're going to find the node in the list of nodes. So self.nodes, right? That's the property where we're storing our whole graph. And we just want to find our current node, which we've stored as a string in this variable. And we're going to just find that current node. And then this expression is a list, right? We've been appending nodes to it with this add edge function. So for neighbor in self.nodes at node, this is a list of each element that is an edge here. And then what we're going to do is we're just going to say toVisit.append neighbor. And that's basically the whole thing. So you'll see that this is the pre-order. So if we run this, you get A, B, C, D, E, G, and F, but you don't get Z, X, or Q. So that's how you traverse a graph.